Hi, this is Kan-Lin speaking. I'm from the National United University Department of Energy Engineering. In this section, we'll talk about the mass transfer limiting current, the characteristic of the mass transfer limiting current. We may consider the balance between the kinetic control mode and the mass transfer control mode. Let's see, for the mass transfer limiting current, we also can see from this diagram like before, when we step the electrode potential, gradually the concentration will keep changing, concentration profile in the solution. But because this one is at the agitation solution, the electrode rotate, so the mass transfer, the concentration profile will not penetrate into the solution at all. It will keep a certain so-called nurse diffusion boundary layer, will keep at a certain location. The concentration profile will not penetrate as the time go to further and further, like linear scanning photometry or cyclophotometry. They won't behave that. So, but when we step the electrode potential from 0 at the equivalent to E1, E2, E3, and E4, the behavior, the concentration profile is shown by this diagram. And then if you plot the current against the voltage, then you end up with this this curve. So when at the E1, at the 0 here, there's nothing happen. The solution is uniform, and the E1, E2 gradually the current is increased. To the E3 is reached to the mass transfer limiting current. So if you increase the E4, E5, they still keep a flat here, will not be changed. And then this current we call the mass transfer limiting current. The current only can be affected by you increase the electrode rotating speed or change the concentration. So the limiting current from the previous, we can see the limiting current equal to 0.62 NFD 2/3 the mu minus 1/6 omega 1/2 and Cp. The omega is the electrode rotating speed in the radius per second. And this is kinematic viscosity diffusivity. In a normal for given electrolyte, this is almost constant, only depends on solubility, concentration, and the electrode rotating speed here. So if you run at a different rotating speed, you end up with a different polarization curve, like this, omega 1, 2, 3. You increase the electrode rotating speed. And you can notice in this region, actually, you increase the electrode rotating speed. There's nothing change here. All the current coincide. This means in this region is a so-called kinetic control region. In this region, the mass transfer is so big. Actually, the problem is the electrode reaction at the surface is slow. So we can express the kinetic current equal to NF, the rate constant, and then Cp. The Ke is a reaction rate constant. It depends on electrode potential. So as the electrode potential become more positive, go this direction, then will be increased. So this one come out increase. The other distinguished area is in this region at a high potential region. Over here, you increase the potential, nothing gonna happen. And this one is called the mass transfer limiting control, because over here the mass transfer rate is small. If you think over here, if I keep increase the potential, the current should be much higher sky around here. But actually, the current is only at this level, because at this rotating speed, the mass transfer rate is somewhere around here. So even your electrokinetic current may be up to here. Now it's limited by the mass transfer rate. And the limiting current equal to NF, Km, and Cp. This is the mass transfer coefficient here. So over here, when you move the electrode potential, scanning electrode potential linearly from here to this direction, then it will move from the kinetic control into the mass transfer control region. If you pick for a given in a mass transfer control region, and then you pick for a given voltage potential, and then you plot the current as a function of electrode rotating speed, you might end up with a linear plot like this, because the limiting current depends on square root of rotating speed. So you got limiting. But at a rotating, according to this equation, you at a 0 rotation speed should be the limiting current equal to 0. In reality, it's not, because at a stagnant electrolyte, even electrode is not rotate, the mass transfer rate will change from the convective mass transfer into the diffusion. The species still will be diffused to the electrode surface. So you still see some small current, but this one much small because of diffusion in the diffusion control. And over here is a convective control, so the current is much bigger over here. But if you increase the rotating speed much higher from the omega 4 and omega 5, you can see at here the electrode rotating speed increase, they kind of more or less equal space increase. But up to here, you increase the increment getting smaller, eventually they diminish, because if you plot the I limiting current against omega 1/2 in this region, actually deviate from this linear behavior, because it will shift from the mass transfer control region. This is the mass transfer control region. If you plot the omega 1/2, in the lower rotating speed is the mass transfer control. The diffusion current or mass transfer current is proportional to omega 1/2. But at a higher rotating speed, you shift back to the kinetic control. Eventually, it's independent of the rotating speed over here. So gradually it's a level out, something like that. In this one, become the kinetic control. Over here, you had to increase the electric potential further, then we go back. So the kinetic control, mass transfer control, actually based on two factors. One is the electric potential. Second is the rotating speed. So from here, for a single rotating speed, you change the potential, it will change from the kinetic control into the mass transfer control. But if you fix at a potential, given potential, you change the velocity, then it will switch from the mass transfer control into the kinetic control, something like this. Now we're going to talk about the KL equation. The KL equation is given by this, this current equal to kinetic current plus mass transfer current. That has some kind of relationship in this way. The kinetic current we are talking about is by the NF, KE, and CB. The KE is like a Tafel equation. The rate, it depends on the electric potential here. And the mass transfer limiting current here is given by from previous the mass transfer coefficient and substitute in there. Let's see how it's derived. For a current, for a given current, this current equal to the mass transfer rate, mass transfer coefficient times the concentration difference between the surface and the bulk. And then at the limiting condition, this means surface concentration equal to 0. Then from here, we can see if we divide by I limit, then you end with the NF, Km will be cancel each other, end with the C bulk minus CS, and then the denominator was CB, and then can further reduce to this. And then you can rearrange this end with a CS over CB like this. And then for the current, this is equal to diffusion rate, also equal to kinetic controlled region. The kinetic rate constant times the surface concentration. If I divide this equation both by CB, multiply CB and divide by CB, they cancel each other the same. But over here, the CS over CB, I can substitute this equation in there, end with limiting current and guess the current here. And this one is a kinetic current. We defined this as a kinetic current here. So we end up with this equation. And this one you rearrange, you end up with this called the KL equation. Let's see what it will happen, what it will come out. We can get an application for this equation. This one, we run a typical rotating disk electrode. We run for instance, at a given rotating speed at 100 RPM. Then the electrode potential scan from minus 200 millivolt all the way to say the 350 millivolt over here. Then we run the same experiment, run at a 400 RPM. This is like a slow scanning rate, linear scanning voltammetry, LSV at a very low scanning rate. We scan the electrode potential again, we record the current as a function of potential again, and then 900, 1600, 2500, and 3600. The reason they pick up this kind of rotating speed because the current depends on the square root of rotating speed. So 100 you take the square root is 10, and this is 20, 30, 40, 50, and 60. So in this case, you end up with a linear. That you got an equal space of the mass transfer limiting current here. Then based on this equation, so if we pick at a one given potential at a 0 millivolt, we plot the reciprocal of the current here. We got the current, and then we plot the reciprocal, the current, against the rotating speed here. Then it should be give a linear equation because this is intercept and this is slope. We end up with this. Then at the other location, we pick up the current here, the current over here, and then we plot reciprocal of this current against rotating speed. Then we got another linear plot, and they should be all parallel because the slope of this are given by this, and then the intercept is a kinetic current, will be depends on the potential. With this equation, we can actually extract the pure kinetic current because over here there's a mixed control from the mass transfer control and the kinetic control all mixed up. So with this one, you can use it by previous section in a linear scanning voltammetry. We go through the mass transfer correct Tafel plot, but also with this LK analysis, if you plot the user rotating disk electrode, you carefully control the mass transfer rate and then plot it out. They can extract the pure kinetic current at the intercept. So this one actually you might think is a mass transfer correct kinetic current. From here, if the IK plot against the electrode potential, then you can get a pure Tafel plot. And then from the slope of this equation, the data, you can end with the concentration of here if other parameter you already know. So this is some we can extract from this KL analysis.